Can everybody hear me back there? Good. All right. We'll take attendance today, so please pass the attendance sheet. When you get to the very back, pass it back forward. All right. So last time we talked about sorting. We mentioned that sorting is a very ubiquitous operation. Many operations in the computer do sort in various ways, implicit and explicit. Most CPU cycles end up being wasted on sorting or consumed by sorting. It's really a waste, and so we study sorting a lot. And it's also an archetypical set of algorithms and algorithmic techniques. So it kind of highlights ways of solving lots of different types of problems in algorithms, not just sorting. So we talked about a lower bound for sorting. We said it's n log n because if the data is unique, it results in possibly n factorial different permutations of a unique set of integers. And every path in the computation will result in a different output, potentially. And so the width of the tree, the decision tree, is not a data structure. It's representing the decision tree, the if-then-else's kind of decision inside the algorithm. The width of that tree is n factorial, and so the height must be a minimum of the log of n factorial, because it's a binary tree, log base 2 of n factorial, which is n log n. Everybody good with this lower bound? So that means no sorting algorithm can operate in general faster than n log n if what you're using and consuming and counting is comparison, pairwise comparison. Okay? You can go faster in special cases, and we'll talk about that. But those are not general sorting algorithms. They're very specific. Okay, so this proves non-existence of any faster algorithm than n log n. It's a non-existence proof. We're proving it without a millionaire. It's not easy to do, but in this case, it's not too bad. Anything can fit on one slide, almost by definition, is not all that complicated. So there's lots and lots of sorting algorithms. There's hundreds of them. Here I'm listing the top 50. The ones in red will go into more detailed, beginning now. And there's many others, and there's reasons why we want so many sorting algorithms. Why don't we just have one sorting algorithm? And we pick the best one, stick with it, and forget about the rest. Well, so there's always a catch, right? There's no best sorting algorithm because you have to consider other factors. So, for example, some have a good worst case behavior, but not so good average case behavior. Some have good average case behavior, but the worst case behavior may also be. So you have to look at the worst case, the average case, how it works in practice. Some theoretically have a good bound algorithmically in terms of big O notation, asymptotically. But in practice, the constant in front of the big O is so high that it's not practical or not practical in certain scenarios. Also, it depends on the input distribution. If you're sorting a very specific input distribution, set of data, you may want to pick one algorithm over another to sort that data. For example, if your numbers are all zeros and ones, and you're trying to sort the zeros and the ones in order, don't pick merge sort. Just pick counting sort, and that'll be a lot faster. If the data already has some sorted properties, if it's near sorted or sorted ascending or descending, or is the juxtaposition of two sorted lists, you may want to pick one algorithm over the other in cases like that, and that'll be a lot more efficient. For example, if the data is already sorted, the sorting algorithm is very simple. Just don't touch it, don't sort it, it's already sorted. Right? That you can do very, very quickly. Also stability. A stable sorting algorithm is an algorithm that if there's non-uniqueness in the data, if two items are the same in the data, the original order of the two items in the input is preserved in the output. In other words, the sorting algorithm doesn't do this. It doesn't flip them around. That means it's a stable sorting algorithm. That's what stability means. You preserve the original order if it's not unique, if they're identical. And that's important because you may be sorting on different fields and different passes. So first you might be sorting by last name, Then the second pass, you might be sorting by first name. And then the third pass, you might be sorting by age or zip code. Because a lot of people have the same names. A lot of John Smiths, right? In China, I guess there'll be a lot of Rongs around. So still, you want to sort them in certain types of passes with different fields in each pass. So stability is important in that case. Okay? You don't want to mess up the previous field if you're sorting on the next field. You want to sort within all the items that are identical on the first field. Within that, you want to sort by the second field in that group and so on. So stability is an important property. There's actually machines, physical machines, mechanical contraptions that actually sort, like key punch cards. How many heard of key punch cards? How many used key punch cards? I did, but I guess that's because when I was using key punch cards, I guess most of you weren't even alive, so consider yourself lucky. It was very hard to do. I can tell you lots of stories about that, but I won't digress about that right now. But there's machines, mechanical machines that sort, actually. And that's even more important how they sort, what algorithms they use to sort. Actually, the postal office still does this with envelopes. It sorts envelopes by zip code, and then delivers that zip code to that city, and then within that city they sort it by neighborhood and so on. So there's actually still mechanical machines that sort. In situ means in place. In place is important for a sorting algorithm because sometimes the data is so large, so massive. You know, we're in an era of big data now. Data sets can be not just terabytes, they can be petabytes or even larger. Google is dealing with exabyte type data sets. So does Facebook, so surely most companies now. When the data is so large, you don't want to have to make a copy of it in the process of sorting. Because just copying a terabyte over USB 2 or USB 3 speed is many hours or even days, just for 1 terabyte, never mind a petabyte. That's not sorting, this is copying it. So a sorting algorithm that needs to copy the data to a buffer, to an array, or to a temporary location while it's sorting it is going to lose out big, such a scenario. In fact, it's not usable at all on big data. So it has to be in situ. It's got to sort in place without actually having to copy the whole thing first or even partly. So considerations like that are very important. And also, you know, if the data is randomized and you're trying to sort it, there's all sorts of tricks you can do versus if it's near sorted. And sometimes some algorithms run better on randomized data than on sorted data. And sometimes it's the other way around. Some algorithms for sorting behave much better, much faster, more efficient if the data is already pre-sorted. Others, if it's pre-sorted, they'll take a long time to sort it, strangely enough. And we'll get to that in detail. The stack depth, if the algorithm is recursive for sorting, like merge sort or quicksort or a bunch of others that use recursion, the stack depth is important because that takes a lot of time to dive deep into the data set as you divide and conquer it or whatever it is you're doing to it. And so that affects your decision of which sorting algorithm to use in that scenario. It's an internal versus external sort. Internal means you're sorting in RAM. Everything is in memory, it's a fast memory. Okay, so you use some sorting algorithm because it's already RAM resident. Access to it is quick. But if you're sorting when the data is on disk, that's a whole different story. Because disk accesses are very slow compared to RAM accesses. And then you want to minimize the accesses to the data, not just shuffle the data around any old which way. And so the optimization you're doing while you're sorting is very different, whether it's sitting in RAM or disk, or worse, if it's sitting on a cloud. That's worse than disk. It's got to go over the Ethernet, long distance, to fetch data back and forth. That's even slower than a disk. We already mentioned a couple lectures ago, how much slower is a disk than RAM to access a single data item, a single byte or word. How many zeros are we talking about? How much slower is disk than RAM, than random access memory? But 7 orders of magnitude, it's huge. It's not just 10 times or 100 times or even 1,000 times, it's millions of times slower. So it's very, very important whether it's internal or external kind of sort. Another thing is whether it's parallelizable or pipeline compatible. You know, if it's parallelizable, if you have multi-cores, they can divvy up the work and all collude in a good way and to sort the data. Okay, but if it's not a parallelizable algorithm, that is not possible. And so you won't be able to leverage multi-cores or GPUs or highly parallelizable architectures, parallel architectures. And if it's not compatible with a pipeline architecture, again, you have to worry about which sorting algorithms are compatible with whatever architecture you're using to sort the data. Locality. Locality means you're focusing on a small subset of the data at a time, right? And sorting that, and then focusing on some other set, and only that set is the working set that has to be RAM resident or fetched currently. In other words, you're not wildly touching all the data all over the place, randomly or haphazardly. So the locality of the sorting algorithm also matters a lot when you have big sorting jobs. And that affects your decision of which algorithm to use. And whether it's online or not, some data sets need to be sorted and maintained sorted. And when new data come in, they have to be added to the data set in a way that keeps it sorted. That means the algorithm for sorting has to be kind of online. It has to accommodate new data coming in continuously and still keep all the data sorted. In other words, it doesn't have access to all the data all at once up front, because not all the data is even there all at once up front. It's trickling in. So some sorting algorithms have this online property, but they work really well with new data gushing in continuously, and they keep the whole set sorted. Others can't do that. They have to start from scratch, and that's not what you want to do when you have big data sets. And there's other considerations. I'm just giving you, the top, dozen or so major considerations that affect which sorting algorithm you would choose to use in what scenario. It gets very tricky sometimes. And sometimes it's not obvious at all. And we gave some extra credit problems involving sorting and sorting-like operations. And how many worked on that? Sorting the ratios of integers? How many have a solution? Linear time solution? One person? Okay. I did not insult your intelligence by giving you these problems. So keep working on it. If only one person got it, or only 10 people worked on it out of 100, we're not going to discuss it here. It's too early. Right? Also, find the majority element if one exists. Be 1, 2, or 0 majorities. So, and then do that only with equality, not with total ordering. And find the max and next to max with the least number of comparisons. And we talked about that last time. How many worked on that one? Then here we're counting it exactly. I appreciate that a couple dozen we worked on. How many have a solution? Okay, a lot less than worked on it. That's okay. That's why we're here, to work on problems and eventually get insights into these problems. But I don't want to just blurt out the answers to these, because I would then deprive you of the opportunity to improve as problem solvers by thinking really hard about these problems. I'm not gonna do that to you.
So what is the space involved for this problem?
So its space is unbounded. But if you're going to do it quickly, you won't be able to use more space than you have time to use. So if you want to use a linear time algorithm for this, the space is not going to be more than linear time. Because even initializing that super linear space, more than linear space, will take more than linear time. Of course, there's a few exceptions. I don't want to make that as a hard rule, but most of the time that's the case, that the space doesn't exceed the time. Because just initializing it will take more time than that. Of course, there's also tricks about using larger spaces without initializing it, but that's even trickier, and we'll get to that in due time. That's much more subtle. Good question. But if the space is not specified, you take whatever, if you only have a time bound, but not a space bound, you can use whatever space you want within that time. If it's vice versa, if I say do it in linear space, you can use whatever time you want. But you have only linear space or constant space or whatever that is. Sometimes, but often I will give both. Like we have problems, we already saw a problem like with the linked list. We use linear time and constant space, I said, and we saw a solution to that. We find the circular linked list versus a linear linked list. All right, let's go through some sorting algorithms. I assume that most of you have seen these before, so we're going to go reasonably quickly, spend just a few minutes on each. But I want you to at least see it once and maybe see it animated. Maybe you haven't seen it animated. A bubble sort basically keeps swapping adjacent pairs. Swap adjacent pairs, and if the pair is out of order, swap it. If it's out of order, swap it again, and keep going. Just keep swapping pairs. scanning the list and swapping pairs that are out of order, and at the end, everything will be in order. And then you don't have to swap anything anymore, and you're done. Okay, so diagrammatically, it kind of looks like this, and graphically, it looks like that. So here's the random data set, and we're swapping pairs. And as we swap in pairs, it falls into order, bubble sort. And here's more specifically the 5 and the 1 will get swapped, and so on. So by the way, the x-axis is the value, the index of the item, and the y value is its place in the sorted list. So if the first item is in the first place, and the second item, second next highest item is in the second place, you get a straight line. Otherwise, you get a cloud. How do you understand this kind of animation? Good. So by looking at that, you can sort of almost tell what kind of an algorithm is running on the data you can sort. So in terms of pseudocode, it looks like this. For I goes from 1 to n minus 1, if a pair, adjacent pair I and I plus 1 pair are out of order, swap them. And by the way, we can sort something ascending or descending. It's really the same thing. If I give you an algorithm that only sorts things ascending order, lowest to highest, but you want to sort a bunch of numbers, integers, descending order, highest to lowest, how can you exploit that first algorithm to do that job for you? Change the sign of all the data, feed it to the first algorithm, get the answer back, and then change the sign again. That's it. How many get that trick? Okay. So without also generality, if you have an ascending sorting algorithm, you automatically have a descending sorting algorithm with only an expenditure of linear time. And you don't even need extra space. You can do it in place, in situ. So without also generality, we can only talk about ascending sorting. Another Jedi trick is if I give you a bunch of numbers and they're not unique, and you have a sorting algorithm that can only handle unique integers, how can you exploit that algorithm that only handles unique integers into sorting data sets that are not necessarily unique and keep it stable on top of that? Or let me ask you a different question. Let's say you have a sorting algorithm that sorts any set of integers you want, unique or not unique. But it may not be stable. Some data that are equal in value could be swapped by this unstable algorithm. How do you convert that unstable algorithm into a stable algorithm? Pretty easily. Not necessarily as a black box subroutine, but a very minor modification. And I didn't tell you what the sorting algorithm is, I just told you it's unstable. How do you convert it to a stable one without any asymptotic expenditure of time or space?
You can add the index of it.
Yeah, add the index of the item and use that as a secondary key to break ties. So if two items are the same value, like 13 and 13, well, you see that they're the same, but instead now that you see two items are the same, compare the indices of these two 13s in the original data, and they won't be the same because the indices are all unique. There's item 1, item 2, item 3. So this is the first 13, that's the second 13, or maybe it's the 7th and the 12th 13. Not necessarily the first and the second, but the first 13 will always be sorted less than the second 13, will be considered less than, even though both are 13. You break ties by using the indices, the index of the data in the original set. And now you have a stable algorithm if you use that simple rule. So all you gotta do is go into the heart of the sorting algorithm where things are compared to each other. And whenever they're equal, break ties, have another if statement that breaks ties by the indices and then make it unequal again. So you never have to encounter equality, just inequality now. How many get that trick? So you can always surgically modify any sorting algorithm that may not be stable into a stable one. And you can use the same trick to modify any sorting algorithm that can sort only unique data. You can trick it into sorting non-unique data perfectly well by the exact same trick. Two things are unique. Inside the inner loop of whatever sorting algorithm it is, look at the indices of those two unique, two non-unique, two equal pieces of data, and by the indices break the tie, and now they're no longer unique. One is less than the other, because the index of one is less than the index of the other. Okay. So whenever you have an algorithm that can sort only unique items, you can easily convert it just by this very trick we just mentioned into sorting arbitrary non-unique items. So without loss of generality, we can say, always consider the inputs to be comprised of unique values. All the values are unique. Everything in the input is unique. There's no duplicates. And then construct algorithms, analyze their time, and so on. And then whenever you have an algorithm that can only handle unique inputs, you can always convert it to algorithms that can handle arbitrary, non-necessarily unique inputs using this trick by breaking ties based on the index. And you won't suffer at all for time or space, because this extra trick doesn't take any more time or space. It's just another if statement in the inner loop. And you already executed an if statement to compare something, now you're executing it again. So maybe you lose a factor of 2 at most in the execution time, because now there's an extra if, but only if things are equal. So it's a factor of 2 at most, and asymptotically it's the same as the original asymptotic running time. So without loss of generality, it makes it easier to design algorithms if you consider that all the items are unique, because you don't have to worry about the third case. Either one is less than the other, one is greater than the other, or nothing. Those are the only 2 cases. You don't have to worry what to do in the third case when they're equal, some special handling inside your code or your analysis or your time complexity. You don't have to worry about any of that. It makes it easier to design the algorithm, makes it easier to analyze the algorithm. How do you understand all that? Any questions about that? So these are now meta heuristics or meta algorithms that help you design algorithms by not having to worry about special cases when you have these kind of insights. So always kind of think like that. Well, if the data is way out of whack, every item is like linear amount of distance from where it should be, so it's exchanging things like bubble sort only moves it one at a time to its intended destination, but no farther than one at a time per iteration. So a lot of migration can happen. And each item can be migrating a linear amount of time, and there's n items, so it can be n squared worst case, this thing. The worst case will occur when? When will this behave as bad as we can imagine? N squared. When it's reverse ordered from the order you're trying to get it into. So everything will have a long way to migrate right across the data set. It'll be n squared. When's the best case behavior? When it's already sorted. So you have basically a double loop and keep swapping, but when it's sorted, one full iteration of the inner loop will not swap anything, and then you know you're done. If you went through a complete scan of the data and nothing got swapped, you don't have to continue. You can stop right there because the thing is sorted if nothing gets swapped over an entire linear scan of the whole set. Any questions about this? It's pretty straightforward. It's got a bad worst case behavior and a good best case behavior. It's stable because things will not get out of whack from the original order. It's in situ, it's in place. It doesn't take any more space than is already used by the data that you're given, because you can keep swapping them in place, assuming it's one big array that you're given. But it is slow, and it's quadratic in the worst case. It's adaptive. Adaptive means sometimes it'll be faster, sometimes it'll be slower, but it'll be a function of the input itself, whether it'll be faster or slower. The time will vary based on how unsorted the data is, or not necessarily how unsorted, but how the structure of the data. Unsorted is one piece of structure a data can have. Sorted is another. Randomized is a third. 2 adjacent sorted lists is another one. And a lot of values get repeated. That's another particular trait that a data set may have. But this algorithm will adapt to the data. That's a good thing. So if it's already sorted, it won't take much. In fact, if it's already sorted, how fast will this run? It's already sorted. The data. Yeah, linear time can be done very quickly. Okay. If it's completely out of whack, reverse sorted, then you'll take quadratic. Of course, if it's reverse sorted, you can check to see if it's reverse sorted, and then just swap, you completely flip it, and then be done quickly. But that's another extra check that won't hurt you asymptotically, but it'll just take time. So you can play tricks like that, but it won't improve the worst case time. What do you think the average case time for this is? We're not going to analyze it here, but it's not hard to do. What do you think the average worst case behavior of this algorithm is? Is it linear? Is it n log n? Is it n to the 3.5, or to the 3/2, maybe n square root of n? Or is it as bad as n squared also, an average? Assuming uniform distributions of the inputs. In other words, all inputs are equally likely. How many say n squared? How many say less than n squared? Yeah, the intuition is correct. It's n squared. It's something that needs to be proven. It's not completely obvious, but it is n squared. Average. So it's pretty bad. When the average case is quadratic, not just the worst case, it's not so good. But it's a simple algorithm and easy to implement, just a few lines of code. It's hard to go wrong with the correctness. And in fact, if the data set is small, you may want to use something like this. So just because it's n squared worst case doesn't mean you never want to use it. If you only have 5 things to sort, actually this will be a lot quicker than Quicksort. How do you understand that? Quicksort has recursion, has to allocate stack frames, Ponder has the extra work, and go sort of recursive. We'll get to that. Okay, odd even sort. So this is a lot like bubble sort that we just saw. It was invented by Nico Haberman from the Turing Award winner at Carnegie Mellon back in the day. But the idea is to swap pairs, but not just any old pairs. Swap all even pairs, and then swap all odd pairs. Then swap back even pairs, and then odd pairs. Alternate between swapping even pairs and odd pairs. So swap first 1 and 2, and 3 and 4, and 5 and 6, but then swap 2 and 3, and 4 and 5, and 6 and 7, and so on. That's almost like bubble sort, but a little more structured in the way that you choose to swap things. Now, why is that an interesting algorithm if you already have bubble sort? Well, because it's highly parallelizable. So you swap the even pairs and the odd pairs. That means when you swap even pairs, a lot of processors simultaneously can swap even pairs and not interfere with each other. And then when you swap odd pairs, you have a lot of processors all simultaneously in parallel accessing the same data, the same RAM, swapping odd pairs, and they don't interfere with each other either. But if you swap an even pair and an odd pair, one processor may want to do this, and one processor may want to do that, and then you can get inconsistent clashes and even overwriting and weird behavior that you don't want, error conditions and all that. But if you swap pairs, you can do them without interfering with the other pairs, as long as you alternate even out, even out. How many understand that? Okay, so it's a highly parallelizable version of bubble sort, and it works really well on near sorted data. It works not so good on reverse sorted data. It is adaptive, it is stable, it's in situ, but it is parallel. Bubble sort by itself is not parallel as it stands. This one is. Okay, so that's kind of a variation on bubble sort. Selection sort. Basically, you find the largest item in the array, and then you put it next. You find the next largest remaining numbers in the array, and you put that second. Okay, so n squared time worst case. It is stable, you can do it in place, it's in situ, but it's not adaptive. This is oblivious to the structure of the input data. Bubble sort wasn't. It adapted to the data and ran faster on some data. This runs the same speed on all possible data, and that speed is always n squared, so it's not so great, but it is simple, and among all the quadratic sorts, it's really fast compared to all the other quadratic sorts. N log n sorts beat the heck out of this one, but among all the quadratic sorts, this is not bad. In fact, you may have used this in your personal life. When have you used it personally in real life with your hands and not with a computer? This kind of a selection sort. Cards. If you play cards and you got a poker hand or play bridge or whatever, you want to sort them by increasing size. You pick the highest card, you put it first, the next highest second, and you're basically doing selection sort right there. And not just cards, whenever you have to sort, a bunch of papers or documents or credit cards or whatever, and you have a stack of them and you want to sort them by some index, you're doing selection sort. So you actually do this in real life. I mean, in real life, when you're playing cards, have done Quicksort. Exactly. That would be funny, right? Because it'd be silly. You know, you'd be like, he'll tell you, okay, hold on a second, I'm recursing for the third level in, you know, and they'll probably just kick you off the table. Never invite you for the second time. So even though it's faster, but it's not faster when you just have a few items, like 5 cards or 10 cards. It'd be, you know, if you had a hand of, you know, 10,000 cards, that wouldn't be a practical human game, but you know, some computer games are like that. Yeah, Quicksort will be much faster than selection sort. You don't want to do selection sort then on 10,000 cards in the hand. I guess that's just a big box of cards. So think in real life what kind of sort you're doing in what situation when you need to sort something in real life. Okay, any questions about that? So this is what it looks like. Obviously, the tail remains sorted as you keep picking larger and larger items. So these diagrams very nicely depict the actual structure and execution of the algorithm very visually. And after a while, when you see enough of these kind of diagrams, interactive animated diagrams, you should be able to tell what kind of sort it is just from the animation. And later I'll show you a few animations. You tell me what sorts each one represents for the same data. All right, insertion sort. Basically, you take the items one at a time and you keep inserting them in the rightful place, you know, in the already sorted items. So sometimes when you play cards, you might actually use insertion sort, you know, not just selection sort. That could work too. Okay? It depends on your personal style. But basically, you pick whatever item you're looking at and insert it into the already sorted list. So it looks like this. So these are the ones that are already sorted relative to each other, but they're missing all these values, and each value can migrate to its rightful place. And that's what it looks like in terms of picture. So it's still quadratic. So you get another quadratic sorting algorithm. Works a little bit differently though. And it is adaptive because if the list is already sorted, it may be very fast execution time, just linear. It is stable, it is in situ. In situ means you don't use extra memory, so sure enough you don't. You do it all in the same array that you're given. And it is online. The other ones are not so much online. This one is. If new data comes in, you can handle the new piece of data relatively quickly. You don't have to go through another n squared iterations or anything super linear. Just in linear time, you can just add the new data in. When new pieces of data trickle in over time. And these days, most data sets are of that nature. You know, big data means the data set is not static. It's huge and it's growing. That means new things are coming in, like new URLs for a Google search engine or new friends on Facebook, you know, new users coming in by the millions every day. And you have to keep things sorted. Any questions about that? The time is a little more subtle than just quadratic. It's worst case quadratic, but in practice, you know, if you do a more refined analysis, it's n times k, where k is the maximum distance of any item from where it should be in a final sorted list. Okay, so if you implement this using just a straight array, and you don't have to do this using an array necessarily, you can use heaps and then it'll be faster. But, or high balanced trees and then it'll be faster again. But if you just do it using plain arrays and you shove everything down, like, you know, the hard way, the naive way, it's a little more refined to say it's quadratic in the worst case, yeah, because k could be n. But if everything is only a little bit of distance removed from its rightful place, you may not have to work that hard, because you won't have to shove down a lot of things every time you insert something. How do you get that? So if, of course, you don't know what k is when you're given the data. So that's the trick. But the running time is input dependent. Okay. It's not just oblivious and squared, no matter what, like some of the others were. Any questions about this one? And so it's nice to have the property. So it is adaptive, and you can quantify the adaptation in this way, in the second bullet. That's always nice to be able to do. Heap sort, we keep mentioning that, but here it is formally. Most of these algorithms were invented in the 1960s or even the 1950s, a long time ago, with a few exceptions, which I mentioned. But it exploits a heap to sort. So a heap, we already know what it is. It's the data structure always keeps the max element at the root. And recursively in the leaves, each node has the max element in it relative to the rest of the tree that hangs below that node. So it's kind of the max heap property. And by definition, it's a height balance. You can implement it. It's not necessarily by definition, but you can implement it in a height balanced way. Okay. And if you do, the largest element is always at the root, and the largest element, once you remove that, the heap is restructured so that the largest element is still in the root, to preserve the heap property. So the idea is this: you initialize a heap, and then you keep inserting everything into the heap, and then you keep removing the root over and over and over again. You take the root, you output the value, you remove the root, which is the max element, and what remains is everything else with the max element still in the root of the new heap after it's been restructured. Okay, so if you just insert everything into the heap, then remove everything from the heap, and they come out of the heap in sorted order. How do you get that? So you exploit, this sort exploits the heap property that keeps everything that's the maximum at the top, at the root, and it relegates all the complexity of sorting really to maintaining the heap. All it is, it does n inserts, then n deletes, and that's it. And this is an example of the running time or the execution of a particular set of data. And this one is the first n log n algorithm that we're seeing, because remember, the heap could be implemented as a height balanced tree, ABL tree or 2-3 tree or a black tree, one of those height balanced, or splay tree, one of those height balanced tree structures. It's only logarithmic deep if you have n leaves. So because no insert or delete takes more than log n, doing n of them and then n of the other takes no more than n log n. And it works pretty straightforward. Any questions about that? But we're really brushing the actual heavy duty, heavy lifting of the sorting itself. We're brushing it under the carpet of the heap. Because we already know that heaps work and work in this way and we implement it efficiently with log n maximum per operation insert into delete. And so we're exploiting that. Trouble is, it's not stable. And it's not even adaptive. Because no matter what the data is, it'll still take n log n. It'll never be linear time. Even if the data is already sorted. So you don't have to do anything to sort it because it's already sorted. This process will still take n log n. How many can see that? You see, when inserting everything to the heap at log n cost each, then deleting everything from the heap at log n cost each, and the total time would be n log n, even if the data can't be already sorted. So it doesn't adapt to the structure of the data. It's oblivious. That's just what it does. Good news, it is in situ. You can do it in place. An array could be used to emulate the heap. And if you're not sure how, look it up. But it can. And so it is in situ. Of course, when we say something, a sorting algorithm is not stable, we already know how to stabilize any unstable sorting algorithm. How do you do that? We already mentioned it. Say it again in just a few words. Break ties by the index. So when we say it's not stable, that's not a fatal flaw. It's just a characterization of the algorithm as it stands, just like that in its original template, without modifications. Okay. The modification to stabilize any unstable sorting algorithm, that's a surgical procedure. It's not major surgery, it's minor surgery. But it's surgery nevertheless. You're modifying the original algorithm, just so you understand. The adaptive part, that is its fatal flaw. That cannot be easily fixed. I'm going to get that. Without major rewriting of the algorithm, restructuring of the algorithm. It's not something you can go in and tweak some if statement and all of a sudden it'll become adaptive. No. You can do that for states, for stability, but not for adaptation based on the structure of the data. That's, you need to rewrite the algorithm, or pick another algorithm. However you want to think about it. Okay, that's heap sort. Smooth sort by Edgar Dijkstra, Turing Award winner in 1972, one of the fathers of computer science. How many heard of Dijkstra? Dijkstra's algorithm, one of his famous algorithms. So he also invented a version of heap sort. That you probably didn't know. And here it is. It's basically a heap sort, but it's adaptive. So he made it adaptive. So we just talked about how to make any sorting algorithm stable. We said that's easy. We said it's hard to make it adaptive. He took heap sort and made it adaptive. So now it initializes not just one heap, but a bunch of heaps. And they're called Leonardo heaps, and they're amortized data structure that have certain properties that the bottom line is this sort runs in n log n time, worst case, but only in linear time if the list is already sorted. But it's a completely different algorithm than regular heap sort. It's a special heap sort algorithm that is called smooth sort, and it uses a completely different data structure than regular heap. It's called Leonardo heaps, and there's not just one of them, there's a bunch of them. You have to keep basically a forest of heaps, not just a single heap. It's more complicated, harder to analyze, harder to implement, but it works. It works nicely, and it proved that it does the job. So it's no worse than heap sort, worst case, but better than heap sort when things are sorted or near sorted. It doesn't have to be perfectly sorted. It's near sorted, this will still work in linear time. Any questions about this? So this one's adaptive. The other one wasn't. This one is still not stable, but we already said how to fix a non-stable algorithm to a stable one with minor searching. So that's not such a big deal. The hard part was to get it to be adaptive. How many heaps do you use? Good question. It could be an unbounded number, based on the data. Could be possibly up to a linear number, but it's a lot more than a constant, potentially. And you can look it up and analyze it and enjoy it, but in practice, this is not often used. It's complicated, hard to implement correctly, hard to convince yourself it works in all possible cases. Okay, speaking of Dijkstra, it was such a luminary and he impacted computer science so much. Dijkstra's algorithm for shortest paths is you using it almost every day in your life. When do you use Dijkstra's shortest path algorithm? When did you use it today or yesterday or last week? When you drive. What about when you drive? Your navigation system, when it chooses routes, and Google Maps, when it tells you where to go and how close something is to something else, it shows you a route. That it uses Dijkstra's algorithm all over the place. How many realize that when you drive? Okay. So you're actually using his algorithms every day. So he pioneered software engineering back in the 60s and 70s, invented concurrent programming, invented the notion of semaphores to handle the issue of mutual exclusion. That's a very, very tricky business. We have multiple processors operating independently, trying to access the same resource, whether it's a memory location or a disk or a printer or whatever. It's actually very, very tricky to resolve this contention without locking out some processor out permanently, which is called a deadlock. How many have ever used semaphores or other mutual exclusion operations or primitives, so you know what I'm talking about, or is it used it? Look this up. It's a very tricky business. The algorithms are not complicated. They're a dozen or 2 dozen lines each for these kind of semaphores, mutual exclusion, dining philosophers kind of problems. So the how many are the dining philosophers problem? I see only a few hands, so I'll mention it because you're not a mature computer scientist if you've never heard about it. So dining philosophers, so it embodies the notion of mutual exclusion and contention in the following way. There's 5 philosophers sitting around a table, each trying to eat spaghetti. They have 5 plates of spaghetti in front of them. But the constraint is, to eat spaghetti, you have to use 2 forks. 1 fork is not enough, but let's just say that's true. Okay. So a philosopher can lift 2 forks and help themselves with a mouthful and then put the 2 forks back. But the guy next to him, while he's doing that, cannot eat spaghetti because he needs 2 forks and both of these are being used by these guys sitting there. So this guy has to put them down, and only then can one of these neighbors can eat and then put those down and so on. Sounds simple enough. But what if they're all very hungry and all are going for the forks? And I'm not letting anybody else eat. Because if this guy is using its 2 forks and this guy using its 2 forks, the other 3 can't eat for an arbitrary long period of time. So you have to have a protocol, a mutual understanding among the 5 so that everybody can eat something and nobody will starve and die and be a dead philosopher, not a living one. That wouldn't be good, even philosophically, that's not nice. So there's gotta be a protocol where each philosopher gets a chance to eat without having to wait an arbitrarily long time. And they all have to execute the same protocol. It's a protocol. Protocol is just another name for algorithm. Okay? And this is not easy to do. As simple as it sounds, if you think about what rules should all of them follow, the exact same set of rules, what set of rules they should all follow to make this true? That each one will eventually eat, not go for an arbitrary long time. There's not even a small chance that they'll go for an arbitrary long time without eating. And preserve that property. It's not easy at all. In fact, it was unsolved for many years until Dijkstra solved it. And you can do it using semaphores or other mutual exclusion primitives. Anyway, he also advocated structured programming. He's the guy that came up with the notion that go-to is bad. He wrote a famous letter to the ACM that essentially was a paper called "The Go-To Considered Harmful." How many heard of that paper? And that gave rise to structured programming. And now it's frowned upon to use go-tos in your code. How many heard of that? You can't use, shouldn't use go-tos. Even though you can, it's there. You shouldn't use it. It's bad. Because it makes spaghetti code. No pun intended. Spaghetti that philosophers eat. So he wrote, the title of the paper was "Go-To Considered Harmful." Of course, there was a lot of debate about that, and if you take it to an extreme, sometimes it can backfire on you, and so other people wrote papers called "Dijkstra Considered Harmful." And the debate still goes on to this day exactly what's the best style to program in, and that ushered in object-oriented programming, where you don't just use go-tos, you don't use a lot of other things, you hide a lot of other things, not just direct jumps. And we still have debate about that. I actually heard him speak once at UCLA in the 1980s. That was an interesting experience. He was pretty esoteric guy. But people put up with him because he was so smart and influential. Okay, so he also famously said things that I'm not sure if he meant them to be funny, but they're funny when you read them. So, he said, for example, the use of COBOL cripples the mind and therefore should be regarded as a criminal offense. The language COBOL. He probably didn't mean that one to be funny, but it kind of is, and there's good reasons why it's actually sort of true. Some things were very insightful. He said computer science is no more about computers than astronomy is about telescopes. So when you hear about computer science, and they all are computer scientists, or aspiring to be computer scientists, and you think it's all about the computer. No, it's not, actually. Computer is just a tool that we use in the field of computer science, but it's much, much bigger than that tool. And a lot of people from outside computer science don't get that. In fact, a lot of people in computer science don't get that either, so we can't blame the outside. Think about it. Astronomy is not about telescopes. It's a much grander field about the origin of the universe and how stars interact and the force of gravity, and on and on and on. And a telescope is a tiny little tool. Well, it's not tiny, it's big, but it's just one simple tool that we use to explore all the other facets of astronomy that are much more important than the telescope itself. It's also about spacecraft and planetary exploration, and lots of other things. So computer science is much the same way. It's not about computers. Sometimes maybe it should be called computation science, not computer science. But anyway, we digress. But another insightful thing that he said is testing shows the presence of a bug, not its absence. That's a very profound statement if you think about it. You cannot test and test and test and then declare a piece of code correct. No. All it means is you couldn't find a bug. Doesn't mean I can't find a bug, or a team of 1,000 smart programmers can't find a bug either. It means that you couldn't find a bug. But, don't get me wrong. It's good to test code. You shouldn't just not test it and release it to users. No, that would be even worse. Okay, but testing, no matter how extensive, no matter how long you test, doesn't show the presence, assuming it passes all the tests. It doesn't mean there's no more bugs left. Okay. All you can do is find them. You can't prove that they're not there by not finding them. It's like proving that you're a millionaire versus you're not a millionaire. It's a non-existence. It's hard to do. So a lot of people forget that, you know, or discount that, or don't understand the value of that, or the importance of that notion. And that's when you have all sorts of bugs in your smartphones and appliances and computerized platforms. And you wonder, you know, how could this have happened? Well, because people didn't think about that, and Apple didn't take this philosophical premise seriously enough. Okay, and that's why we have operating systems, millions of bugs in them, even though we use them every day. Doesn't mean they're useless, by the way. If something has bugs in it, doesn't mean it's useless. That's not what it means at all. A typical operating system has tens of thousands of known bugs and probably millions of unknown bugs. I mean, there's hundreds of millions of lines of code. It's still very useful, and it's still very monetizable and, you know, market practical and so on. Anyway, he harped on simplicity, right? He really, really beat that one to the ground. And all these algorithms were very simple, short, elegant, beautiful. That was one of his hallmarks. What I emphasized from day one in this course. Simpler is better, all things being equal. Getting the job done is nice, but getting it done elegantly, simply, generalizable matter is even more impressive and useful and valuable. And it's directly related to reliability. When you have a machine, whatever that machine is, a car, a refrigerator, a computer, you know, a city, you know, an engine, you know, a plane, when you have a machine, it has lots and lots of parts, compressors and motors and chains and fans and pumps and all sorts of reservoirs and, you know, all sorts of systems inside. Some machines have hundreds of different, you know, moving parts, or even thousands of moving parts. Your car engine has thousands of moving parts. Cams and shafts and pulleys and springs and belts and fans and pistons and hundreds and hundreds of moving parts. My car only has one moving part, actually, right? The electric motor. I guess 4 more parts are moving, the 4 wheels. But the internal combustion engine, hundreds of moving parts, and it fails miserably all the time. A computer has billions of moving parts if you consider all the transistors. I shouldn't say moving in terms of actual motion, but interacting parts, active parts that interact with each other. Whether they move or they don't move, they're still active parts that change state and interact with the neighboring parts and so on. The simplest, most reliable part in any machine, the one that will never fail, the one that you'll never have to replace, the one that's the cheapest, the one that's easiest to design. What is that part in any machine? This is a philosophical question now. Think about it. Think high level, think deep, think abstractly. What's the part in any given machine, an engine, a motor, a system, a plane, a car, you know, any kind of large system or even small system, the part that's the cheapest, the easiest to maintain, the one that would never fail, the one that costs the least, the one that's the most reliable, the one that will never get in the way of the operation of the system or any of the other parts. What is that part, philosophically? And we just talked about it in the abstract.
The part that doesn't exist.
The part that ain't there. How do you get that? On one hand, it's amusing, right? But it's a very deep, serious philosophical and design principle. How many see the subtlety of this? In design, in architecture, in art, even in music, in every field of human endeavor, simplicity is better. Occam's razor, right? You mentioned that a few lectures ago. I remember that because it's so important. So he really harped on Occam's razor, simplicity. The one subroutine in your code that will never fail, that will never have bugs in it, guaranteed. That will never crash, that will never do anything bad or wrong, is that subroutine that's not there because you managed to avoid writing it because it wasn't necessary to begin with, and you realized it while you were writing it and you left it out. Think about that and really meditate on that. wrap your mind around this very tightly throughout your life and career. Very, very important, very deep statement and principle. A lot of designers, a lot of engineers don't appreciate this. And so when they build stuff, they keep adding things. And if something goes awry, and they keep adding more things to fix that one thing. And when you code, you tend to do that too, because it's just another engineering discipline where you build artifacts. So if something doesn't work, you add another something that makes it work or tries to make it work. And when that doesn't work, you just add more and more if statements and conditionals and special handlers and exceptions. No, stop, stand back, take a deep breath, and rethink your whole approach. And you'll see that chances are it can be done much more simply and reliably and elegantly and generalizable if you just stop and backtrack and maybe even rewrite the whole thing if necessary. It's hard to overemphasize that. Okay. And that's why electric cars just have only a few moving parts and they can last almost forever. And they run at ambient temperature, not at hundreds of degrees that like a internal combustion engine. That heat expands and contracts all the metal, creates cracks and metal fatigue, and also wears out all the gaskets and rubber parts and fans and belts that are made of polymers. And there's so much complexity in internal combustion engines. And then you need radiator to keep it cool, and then you need also the lubricants to reduce the friction, and because there's so many parts and they're all rubbing against each other. On and on and on. That's a terrible way to design something to move you around. Awful. And it's on its way out. Within 10 years, most countries, you couldn't even buy one. Norway just passed a law that in 5 years it'll be illegal in Norway to sell an internal combustion engine car. If you already have one, you keep it till it dies, but you couldn't buy new ones. So that's finally the world is wrapping its mind around this kind of principle when it comes to transportation, except a few politicians. I'm not going to name them, but you know who they are. So he harped on these principles, very, very important principles. Okay, let's generalize heap sort. So you don't think it's just about heaps, and it's not. So, basically here's a heap sort regurgitator. Initialize a heap, then insert n things into it, then delete n things from it, then print them out as you go, and that's the heap sort, right? But it doesn't have to be a heap, right? Other data structures can work here too. That's the main observation. So replace the heap with any height balanced tree that you want. You can use any tree that you want instead of a heap as long as it's height balanced. It could be an AVL tree, it could be a 2-3 tree, it could be a red-black tree, or anything else that operates in an efficient way and keeps things height balanced and or log n per insertion and deletion. So the worst case still is n log n, no matter what kind of data structure we use. So for example, we can use B trees or 2-3 trees or splay trees, and that's kind of a form of a heap sort still. It's generalized heap sort, where the heap is not exactly necessarily a pure heap, as you may have known it, but some other structure that preserves this property that a heap does, and it could be a tree of some kind. So just realize that this is a much more general algorithmic template than just heap sort. It's arbitrary, efficient data structure sort, whatever that data structure might be. Okay, and still has the same structure algorithmically. Okay. So here's an example of a B tree sort, and it uses B trees to sort, and it looks exactly like the animation we saw a couple of lectures ago. And the highest element is could be maintained at the top. Now, I'm not preserving the heap for it here in this animation because I didn't want to have to redo this, but it works. And because it preserves the log n time per operation, this whole sort will happen in n log n time. Same for AVL tree. I think here but you get the idea. When they say heap sort, it's not necessarily pure heap. Any questions about that insight? Substitute whatever data structure you want for it, as long as it's efficient and it does the job, you're good. Okay, merge sort. That was invented by John von Neumann back in the late 50s. He did so many other things that giving him credit for merge sort is almost superfluous. But he did come up with this. So this is a typical divide and conquer strategy. You partition the data into two equal halves, you sort each half, and then you merge them together, like you zip them together like that, and the entire thing ends up being sorted recursively. So it's n log n worst case. The timing is embodied by this recurrence relation, so the time to sort n things is twice the time to sort n over two things, that's the two halves, plus a linear amount of work to merge them together, and it turns out that is n log n. We'll prove that in a second. It is stable. It does parallelize. You can sort both halves in parallel using two processors, and then they're each one of the halves of those using more processors. So you can actually employ a lot of processors, but it's not in situ. It's not in place. You have to copy the data over to maybe a second array or whatever, and then recurse on that, and then merge them. The merge step, it's hard to do the divide and conquer and the merge in place. But it can be done with great effort, made in situ. Okay, and that's really hard to do, but it's finally somebody did this many years later. And it's just complicated. So, any questions about how that works? So again, I assume that most of you have seen these. So we go through them quickly. We just mention interesting things about them. Here's one way to prove that it runs in n log n time. The time to sort n things is, first of all, you do a linear amount of work by splitting into two, and then sorting the two halves. So you're doing another linear amount of work on each half, splitting it, and so on. And then you're doing another linear amount of work on the third level, the fourth level, because there's 4 quarters and 8 1/8ths and so on. But each level of the recursion totals a linear amount of work across the entire level. So it's linear amount of work for each level, and there's logarithmic number of levels, because there's only so many times you can divide by 2 until you only get 1 or 2 items. Right? When you want to merge sort 2 things, how do you do that? Well, either leave them alone or flip them. You don't really need to worry or recurse any more beyond that. And there's log n levels times linear amount of time or resources consumed at every level, so it's n log n total. You can also use this recurrence theorem, this master theorem for a recurrence solution. You get the same thing, basically. That's an easy way to see the n log n behavior of this. Any questions about that? Okay. Quicksort. So Quicksort, it basically picks a pivot element, picks some say random element, puts everything that's less than it on its left side, everything that's greater than it on its right side, and then recurses on both pieces. Now these pieces, unlike merge sort, these pieces in Quicksort don't have to be the same size. You're picking a pivot at random, say, and there's other methods of picking pivots. You can pick the best of 3, like the middle of 3 or whatever, but that's the same, pick a pivot that's random. Put everything that's lesser on the left, everything that's right, that's greater than on its right, and then sort both pieces, and then recursively the whole thing will be sorted. Because everything that's less than it in the final sorted list will have to be on its left. So you already put it there. It's already sorted right now before you recurse, but it's in its rightful place with respect to the pivot. Everything that's greater than it in the final sorted list will have to be on its right. Right now it's not completely sorted, but they will still all be on its right, everything that's greater than it. So with respect to it, the pivot, the right side is already in its right place. All the items on the right side are in the right place. Not necessarily sorted amongst themselves, but they're all on the right as they should be. So again, you take 2 sublists, you do this thing, and it's n log n average time. Because on average, the 2 lists won't be too far away from each other in terms of size. It may not be half and half, but it'll be 2/3 and 1/3, or 3/4 and 1/4. Or it'll be maybe 90-10. But it's very rarely going to be 1,000 to 1. Unless when? It's already sorted and you're picking really bad pivots. And most of the stuff is always to the left or to the right. Then you'll get n squared time. It's pretty rare. Okay. So in practice, this works beautifully on kind of random point sets, random sets of numbers. It is unstable, but we already know how to make it stable. Minor surgery. The amount of space it uses is not trivial, it's because there's recursion depth. So every time you recurse, you allocate another recursion stack frame, and you can have log n of those. So even if they're small, constant size, and they could be even larger than constant size, there's n log n of them, so the amount of space can add up if you're not careful. But it's not linear, it's logarithmic if you're careful. Unless you get this worst case behavior, in which case, how many recursion stacks can you have in the worst case when you have really bad data and you pick the wrong pivots over and over again? How deep can the recursion be? It could be n, and that's bad. But there's a way to keep it to log n. And in practice, all this stuff about recursing and stack frames and compilers and do all this extra work, storing and copying variables, it only beats a quadratic sort for n larger than a few dozen, like 30 or 40 or 50. Just like you're not going to sit there in your bridge game and use Quicksort to sort your cards, and you'll laugh when I said that, and rightly so, because it's kind of silly. There's so much overhead in this recursion, and it takes a lot of time. The constant is high in this asymptotic notation. So if you want to sort less than 30 or 40 things, don't use Quicksort. Use anything else you want. Don't even use merge sort. Use insertion sort or bubble sort or whatever. Selection sort. That's fine for a few items or a few dozen items. Quicksort only kicks in when, in terms of value or extra speed, when you have more than a few dozen. If you have hundreds or thousands, certainly if you have millions or billions, you can highly benefit from it. Okay. Let me ask you a question. So Quicksort takes n log n time average case, and most cases are average, almost by definition. N squared worst case. How would you surgically modify Quicksort to give you n log n case, n log n worst case, and avoid the n squared cases almost always? So even if I give you data that's already sorted, and you're going to use Quicksort on it, what Jedi trick are you going to do to make sure it doesn't run in quadratic time?
Choose the pivot and
Just the pivots.
Yeah, you could use better pivots. Let's focus on that for a second. What's the best pivot to use in Quicksort to make sure that the worst case will remain n log n? What ideally, I'm not saying it's easy to do, it is possible to do, and we'll get to that. What pivot do you want to use in the ideal scenario? The median. How many see that? Because then there's equal numbers on both halves, and then it'd be like really, really fast. So why not use the median? Why not implement Quicksort and use the median? Takes a long time to find the median. In fact, it's not easy at all. How fast do you want to find the median to preserve the n log n overall behavior of Quicksort? If you could find the median, how fast should you be able to find the median to make that work? N, not n log n. If you took n log n time to find a single median, and you have to keep finding it at every level of the recursion, overall, it's going to be a lot more than n log n. How many can see that? I hope you can see that. You just use n log n time right at the very first level before you even recurse. So how's the whole thing going to work in n log n? You already wasted that time. So you want to be able to find the median in linear time. How many know how to find the median in linear time, worst case? Nobody. It's a perfect voting record. How many think it's possible to find the median in linear time, worst case, for n unique numbers? How many think it's possible? How many think it's not possible? Nobody's voting. Well, maybe I'm not expressing myself. I'll repeat. Let's backtrack. How would you find the median straightforwardly if time wasn't an issue? What's a simple algorithm to find the median? Sort, and the middle one is the median. Simple. But that's n log n time. What if you only had linear time to find the median? Because you think about it, to find the median, you don't need to sort the entire set. That's kind of an intuition. It's not a proof, it's an intuition. Because when you sort, you're doing a whole lot more work than finding just the one median. You're finding all kth largest for all k. The median is the k over 2 largest. You also find the min, the max, the second largest, the third largest from the end. You're finding all of them. That's what sorting is. And you're doing all that work just to find the middle one and ignore all of rest. So the intuition is maybe you don't need to sort, and it turns out you don't need to sort. So let me just tell you, since nobody voted one way or the other, so it must be news to you, and that's okay, that's why we're here. You can find the median in linear time, and we'll actually see how to do it. It's not easy. That will be probably the hardest algorithm we'll see to that point. And it's coming up probably in the next lecture. Or at most a lecture after that. It's not the hardest algorithm we'll see in this entire course. You can get progressively more esoteric. But finding the median in linear time is not easy, and it was an open problem for several decades. And finally it took 5 Turing Award winners combining their efforts to come up with it. Floyd, Tarjan, Pratt, and a couple others. They're all very impressive luminaries. Anyway, if you could find the median in linear time, Quicksort will be n log n worst case. So far, so good? Okay. Next insight. How would you run Quicksort? Even as a black box subroutine, you can't modify the black box subroutine. It's already coded, it's hard coded, it's executable only, you can't touch the source. All you can do is use it. But you want to avoid these n squared worst cases on data that's sorted or near sorted. By the way, Quicksort will have n squared worst case, not just when it's perfectly sorted, but when it's almost sorted, same problem will occur. How many can see that? If only a few things are out of order, but the rest is all sorted, the same thing will occur. So it's not just one worst case, it's many worst cases. When it's sorted, almost sorted, or the first half is sorted and the second half is reverse sorted, that'll be pretty bad too for Quicksort. How many can see all that? Okay. So it's a lot of different cases that will foil it, that will make it run in quadratic time, which is terrible. Not just one instance, but a lot of different scenarios will make it run really badly. How do you avoid all of it? So that's a subtle question that undergraduate course may not have enlightened you with. But here we are to cross that bridge. Yeah. What do you guys say? Randomize it. So if you take the input and before you feed it to the Quicksort routine, randomize it completely. Then feed it to Quicksort. Then Quicksort most likely, almost certainly will run in n log n time because the data is random. No matter what the original data was, the one you feed to the Quicksort algorithm is random. And any kind of order will be completely messed up. Think about the subtlety of this strategy. How counterintuitive it is. You're trying to sort. You're trying to put something in order. And in order to do it faster, you first need to unsort it. Put it in random order, which is the opposite of ordering. Randomization is the opposite of sorting. How many can see that? It's exactly the opposite. And that'll make it run faster. So randomizing, putting it way out of order, will make the ordering operation faster than if most of it was already in order, which is kind of mind-boggling in terms of counterintuitive notion, but completely true. Any questions about that? Subtle. So that's an algorithmic technique, randomization, very powerful algorithmic technique. And you can use it in many other scenarios, not just here. To make things run faster, shuffle them into arbitrary order first, and then things will speed up. I'm not saying you should do that all the time, blindly and hope for the best. No, I mean, some scenarios, that's not what you should do. That's exactly the opposite of what you should do. So that's an interesting insight. Let me ask you another question, it's even more subtle. There's a bunch of cases that will make regular Quicksort degenerate into n squared worst case behavior, which is really bad. Randomizing the data will fix those cases, but it will unfix other cases that are already random, and the randomization may accidentally put them in order, and then you'll have a worst case scenario, and everything will even out and it'll be a wash. And the average case, the worst case will still be n squared, and the average case, it's you're not going to gain anything, in other words, because this randomization process will arbitrarily fix certain disorders into order, and other times it will fix orders into disorders, and overall you will lose, not win, or at least break even, and it's no point in doing it. How many understand the question? What do you say to that? Is it still worth doing? Or will randomization create as much damage as it will fix overall? Yeah.
It'll fix more damage than it causes.
It will create more value than damage by far. Why?
Because most randomizations of a list are pretty far from sorted.
Yeah, most randomizations of a list are very far from sorted. Another way of saying it, among all permutations that exist on n objects, very few of them are actually sorted or near sorted. Most of them are random. How many believe that? Yeah, intuitively it's right. Let's quantify it mathematically. How many different permutations are there on n objects or unique objects? N factorial, that's a huge number. How many are sorted or near sorted? Well, there's only two sorted ones, ascending and descending. And there's a few with, one item is out of place, or two items are out of place, or five items are out of place, and the rest is sorted or near sorted. There's far fewer than n factorial sorted or near sorted tweaks on a permutation than the rest, which are mostly random. And that's the data set you're creating for Quicksort by randomizing, creating a vast ocean of randomized permutations, and very few will end up sorted if they weren't sorted to begin with. And in real life, most data sets are already sorted or pre-sorted. How many believe that? You already did a lot of work sorting a bunch of names or database, and when you add new stuff to it, it's already pretty much mostly sorted with just the new names that need to be sorted among all the old data. There's only a few new things and mostly old things, lots of old things, only a few new things. So most data sets in real life are already sorted or almost sorted when you need to sort them because of this phenomenon that you have to incrementally build them. So the Jedi trick here, very subtle, again, to create order, first create chaos. I only wish that's what our president is trying to do, but can't now. Very counterintuitive notion, but very powerful. And randomization in general is a very, very powerful technique. We'll talk about random numbers. Let me ask you an even more subtle question, and then we'll finish. Let's say I want to fix the worst case scenario of Quicksort to n log n as well. So I want to preserve the n log n average case, but I want to make the worst case, no matter what, n log n as well. Never quadratic. How many think it's possible? How many think it's not possible? Okay, only a few people voted, and the few that voted said it's possible. How would you do it?
Take the indices of the user as a pivot point.
It won't be just for the indices. The indices can also create very skewed breaks around the pivot, unless you pick the median. So again, let's say you have an n log n average case quicksort algorithm. Let's say you can't even modify it. Let's say it's a black box, you only have the executable, not the source. So you want to run quicksort on a data set, and you want to make sure that sorting is over in n log n time done. Even though quicksort can sometimes take quadratic time, as we said. Even when you randomize it, it's still take quadratic time if you, by accident, randomize it in a way that happens to sort it by accident. You don't want to do that. So how can you run quicksort and leverage the n log n fast expected time and keep the worst case also n log n? So I'm suggesting to you it's possible. How would you do it? That's, again, something that you would not have encountered in the undergraduate course, but we're here to take it to newer and more subtle levels.
If it's already sorted, then go to the
So if it's already sorted, don't run quicksort. How will you avoid running quicksort? How will you know it's already sorted without, or even near sorted, without a lot of checking and wasting time on that? Because that could take some time. What else? Give you a hint. Mendte Heuristic. Use a meta algorithm, which is just another algorithm. But think at a more abstract level, higher level. We already have an algorithm that's worst case n log n, right? We've seen it a couple of slides ago. Which one was that? Actually, we saw several. Deep sort, merge sort. Okay, then what do you do? But those have a high constant. a lot of overhead, and they're running analog n time sure enough, but Quicksort, it runs much faster with a much smaller constant in the asymptotic notation, which gets swallowed by the asymptotic notation, so they look like they're running at the same time analog n, but really, merge sort is much slower than Quicksort. There's a reason why they call one merge sort and the other one they call it quick sort, because it's quicker, it's much faster, on average. But it's a constant. The asymptotic is still analog n. The constant is much smaller than the other analog n sort. All right, so with all that, use that as a hint. How would you use Quicksort and leverage the good asymptotic and good constant of Quicksort and still never take more than n log n time, worst case?
Maybe we can use like filter using the Quicksort, but sort using Quicksort.
Okay, what else? Let me give this one to you. Run Quicksort and merge sort in parallel on the same data. When one of them finishes its job, stop and abort the other. And you'll have your sorted answer. How many can see that? All right. How fast is this average case? N log n. Worst case? N log n. And you still use Quicksort. With the aid of merge sort as a fallback in case Quicksort, it ain't so quick. Okay, you're still using it. And most of the time Quicksort will finish first. But in case it doesn't, and you don't have to know when, the other one will come in and save the day. That's called a meta heuristic. When you combine two heuristics or two algorithms, a meta algorithm, you fuse them into one in this elegant, oblivious way that makes it work. What's the price here? Not a completely free lunch, but it's pretty cheap lunch. What's the price here? What do you really lose? Some space. How much CPU time do you lose? Well, if you have two cores, if you have two CPUs, you do it parallel and you don't have clock time, you don't lose anything. But if you have one CPU that time slices among two processes, and each one process runs Quicksort, the other process runs merge sort, how much time do you really use? You lose if you do that in parallel on a single processor. What factor do you lose? How many say double? At most two. You're running both in parallel. One will stop before the other, and then you stop the other. And if you time slice jump back and forth like processors do among processes, that's how time sharing works anyway. When you have a bunch of processes running on the same processor, the processor basically executes round robin in little time slice here, little time slice there, a few microseconds here, a few microseconds there. They run in parallel, even though you only have one core. Right? How many know that? That's what happens inside your architecture. If you have two cores, all the better. But if you have one core, it's still running a lot of things at the same time. Your iPhone runs, your smartphone runs hundreds of processors simultaneously. Processes of all kinds, not just the apps, but also some operating system subroutines and schedulers and compilers and all sorts of timers. And everything is running simultaneously, like time slicing, round robin, time sharing of the same processor. Anyway, so you lose a factor of two. Why? Because you're running them in parallel on the same processor, and you're jumping back and forth. So the total time needed for one of them for the faster of the two to finish is twice that time of the fastest of the two. How do you get that? Because when it finishes, the fastest finishes, you're killing the slow one, you're stopping the slow one, and it doesn't consume any more resources. So that Jedi trick enables you to combine any pair of algorithms, not just Quicksort and merge sort, not even for just sorting. For other problems too, run two algorithms in parallel. You inherit the good average case behavior of one and the good worst case behavior of the other for free, without modifying either one. And together, that's a new algorithm, and it works beautifully, and it does work. You may have to pay a little bit of a constant in terms of factor of two, but given that Quicksort is much faster than much faster than twice merge sort as fast, because twice merge sort is probably 10 times or or 20 or 30 times as fast as merge. So the factor of 2 is a small price to pay, especially if you don't have to worry about the worst case anymore. Anyway, how many have heard something like this before? Okay, a few. Well, my gift to you. All right, any questions about that? All right, we'll pick it up next time and go deeper into this. See you. Yeah, you can run Quicksort twice with 2 integrations. Smaller chance. The other possibility that what we just suggested gets you the and then quadratic is whatever. But yeah, you can do that too.
4楼有捞，就我们那天去那个。